morning, everyone. On the behalf of Computer Science Department and Engineering, I welcome you all. I welcome on the today's seminar, international seminar on 5G and its association with the artificial intelligence. Our guest of honor for today, Professor Andreas from the Department of Computer Science, University of Cyprus. I welcome DRC Chairman, Department of IT, Dr. Dinesh Kumar Vishwakarma. I welcome Professor Rahul Kataria, Professor Department Computer Science. I welcome Manu Sethi sir, Professor Department Computer Science. I welcome all the other dignitaries present here, students, ladies and gentlemen. Today, 5G and its association with the artificial intelligence has been growing through around the world. As we see, the 5G has launched yesterday in Delhi itself. Today, we are talking about the wireless communication becoming an ambitious and everyday life tool with the user demand growing at extremely fast pace. Despite impressive breakthrough in almost every part of wireless system, from the antennas to the hardware or to the operating software, this demand reaches increasingly challenging to address. Today, Professor Andreas will discuss about the 5G, its association challenges, expect that we can correlate the different domain that we are correlate with it, especially the artificial intelligence. I welcome Professor Andreas. Before that, I request Professor Manu Sethi sir.
Thank you very much. Thank you. Much appreciated.
I request Professor Rahul Kataria from the Department of Computer Science to welcome ma'am. Just moving ahead for the seminar, I want to welcome Andreas Pitsillides. Just before that, he is a professor in the Department of Computer Science, University of Cyprus. He is also the head of Network Research Laboratory and is appointing visiting professor at the University of Johannesburg, Department of Electrical and Electronics Engineering Science, South Africa. His board research interests include communication network, fixed and mobile network wireless, nano networks, software-defined materials, and its application towards communication problem. I welcome Professor Andreas.
Namaste. It's a great honor to be here, and I would like to express my sincere thanks to the Delhi Technological University, the Department of Computer Science and Engineering, and the IEEE TTU Computer Society for hosting this seminar and allowing us to socialize and exchange ideas. In particular, I would like to extend my thanks to the Chief Patron, Professor Jai Prakash Saini, the Patron, Professor Mathur Satan Singh, the Convener, Professor Vinod Kumar, and finally, but not least, Professor Rahul Kataria for organizing this seminar, enabling us to exchange our ideas, hopefully leading to further collaboration. And the topic today will be on a preview of 6G and its challenge. Sorry, this is the next presentation. I'll break the presentation in two parts. The first part is to talk about AI in 6G. And the second one, I will try and give a quick overview of vision and challenges in 6G, at least to amplify some of the problems we see and maybe identify areas of further research. So let me change the presentation to that one. So this is the first presentation. I don't know if our audience can see that share screen, but they'll let us know, I guess, if there is any joining. Without further ado, I would like to start this first part of the talk. 5G, I could add there 6G, of course, but 6G would have its own uniqueness, so we'll focus mostly on 5G and its association with artificial intelligence. The main part of the work was accomplished by my postdoc, Iacovos Ioannou. He graduated last August, and he looked at this framework which we'll focus our talk on. And Christophoros and Vassos are colleagues at the University of Cyprus. And I have quite a few collaborators now on the specific topic of AI and 5G. Of course, here at DTU with Professor Rahul Khattar and his group. Thank you for the introduction as well. NITGO is a good collaborator that goes back 5 years, Pravati Swain. In the University of Johannesburg in South Africa, Suvendi Reimer is another good collaborator who is joined us to be part of this work. And SSN Institutes in Chennai, we've been doing some work there as well for the past year or so. And a recent addition is Jaist Kanazawa with Sahe Travait in a very different problem, which has many similarities though in terms of AI needs, and that's the power system. So basically, it's undeniable that wireless communication is becoming ubiquitous in everyday life. That's even so despite impressive technology breakthroughs in almost every part of our wireless systems, the user demands scaling up and the complexity growth being at an extremely fast pace have increased the challenges that we need to address. And it's clear that technology on its own will not be able to solve our many problems that we are facing, especially towards the management side and the control side. And AI ML, it's a buzz field now. We all have heard about how these techniques have solved problems in so many domains. And in spite of that, their adoption in 5G, 6G is rather slow. So if we go to the problem statement for our case, we are looking at communication networks, in particular mobile communication networks, and we all hear these buzzwords and what we want to do in the near future, what we want to do now. And it's clear that our existing hardware and software, our technology, is not going to be able to cope with all these new demands. If we write it down as requirements for 5G, we'll see some numbers now, but everywhere you look, there is a huge demand on increasing the data rates, lowering the delay, the latency, lowering the energy consumption, having high scalability, because now beyond the mobile users will interconnect the whole world with devices, Internet of Things, etc., smart systems. So we want improved connectivity and reliability to cope with this increasingly digital world. And of course, security goes without saying, and privacy. Even more so for 6G, as we will see, we'll be talking about extremely high demands in what we need to offer in terms of data rates. We're hitting data rates here in 5G in terms of gigabits per second. And when we hit the 6G, we're talking about terabits per second. We're talking milliseconds delay there, we're talking 100 microseconds delay here. So the demands for our technologies are beyond what we can cope with our existing technology. So our existing mobile technology is challenged in terms of the requirements here, huge bandwidth. The infrastructure that we have now cannot meet either the demand for higher data rates nor the connection density that we require in the Internet of Things era. And we need also to address new technologies which increasingly demand and complicate the network management in terms of softwareization on aspect, software-defined networking, network function virtualization, metaverse, augmented reality, virtual reality, autonomous vehicles. All this would require a new approach to manage the new infrastructure that we are expecting for 5G, 6G. So an approach to manage the 5, 6G, 6 riot requirements is to introduce within the network itself, embed within the network itself, artificial intelligence, machine learning. And it's well known that it will have an integral role to play in the 5 and 6G for their management and control. So what we sought to do, that's my postgraduate student Iagovos initially. He sought to find an AI approach that was distributed. We know the communication network is distributed in nature. We have devices, either the mobiles or the Internet of Things devices, which are distributed, and the whole technology is sought to be flat, distributed in the future. So we thought that maybe there is a distributed AI framework we could adopt to handle this complexity. So an agent-based distributed approach would allow us to have agents, AI agents of course, within the very fabric of our network. So just to make sure that one second please, I have a chat here. I think maybe they're not, cannot see. It's, cannot hear the presentation. Don't know if I can do anything now to, okay, we'll proceed. I think we cannot fix problems now of hardware. Apologies for that. In this table, we try and quantify some of these strict requirements we will need in terms of key performance indicators. And the peak rates I mentioned earlier on for 5G, at least we'll be talking about gigabits per second, tens of gigabits per second. Coming over to 6G will require another quantum leap. And if we go back to 4G and 3G, we're talking about megabits per second. We see the gradual tremendous requirements we place on our networks. In terms of the user, we expect to have data rates experienced in the gigabits per second arena, the spectral efficiency to double. And if we go through this table here, all indicators are very tough already in 5G, and they would even become even more for 6G. And we need to consider especially the metrics for 6G in terms of the connection density, the energy efficiency, the jitter, and the reconfiguration. They would definitely need new approaches to be handled, and AI is expected to be one of them to allow the orchestration of the networks in 6G. What we have to address, and we sought to address, is to offer a new framework where we can have a fully decentralized control with virtual resources. We aim that framework to be adaptable and flexible in any situation and support dynamic environments and on-the-fly reconfigurations of the network. We sought new intelligent approaches, especially for 6G metrics related to management orchestration of virtualized networks, such as energy, efficiency, reliability, mobility, reconfigurability. And above all, we want it to be a distributed, intelligent approach so that we can lead to independent and autonomous systems. Self-free is a buzzword that we're hearing lately, especially for 6G. So the idea is to get rid even of the base stations and have a more flat architecture. And we expect AI, ML to be supported everywhere, from centralized to every terminal in the network. And it's been talked about quite a lot what technologies we will need to meet these demands in 6G or even in wireless LANs. And Professor Akildis has a number of papers, survey papers, which identify quite a number of these technologies. And of course, pervasive artificial intelligence, machine learning is one aspect. And we posture that it has to be also distributed AI. So our objective is to develop an agent-based distributed AI framework which will also act as a glue with other AI ML techniques utilized by the mobile entities, and we expect that they can satisfy our 5G, 6G requirements. We'll be able to support self-organized networks and also be adaptable, autonomous, dynamic, and flexible, buzzwords you see in any networking papers, of course. And what we selected as one possible agent type, intelligent agent, is this type of agent which is called BDI. B stands for belief, D for desire, and I for intention. So BDI agent-based AI, we hoped it would be a promising technology worth investigating to realize the above. And we've done quite a bit of work on that, and we believe that there is something that is worth investigating in this area. So BDI agents are based on a concept where intelligent agents can manage their knowledge, abilities, and capabilities by themselves. They have intents and plans like we humans have intentions of what we want to do. We have plans how to implement them. And then we perform actions to realize these intentions and these plans. And we always have an objective which we would like to solve. So much like us humans, these BDI agents would do that, and they would do that either by collaboration with other agents or as individual entities. So why BDI agents? Well, it's because of their unique features, and I already mentioned before, beliefs is what basically we know about our environment. Much like as humans, we know our environment, at least we can measure some things, we can learn about some things, and we can include inference rules, and we can allow advanced training to guide to new beliefs. We can use any type of knowledge here, either extracted or measured through sensors, or inferred through neural networks, for example. And beyond the beliefs, we have desires, which we correspond to what we would like to have. For example, I would like to have a Ferrari, but maybe it's realizable, maybe not. That's a desire that I have, and that's my motivational state to act and do something. And then from the desire, we have an intention. I intend to buy my car. So that's an intention, and maybe I'll have to go through a plan, through a goal, to achieve that, and that corresponds to the deliberative state of the agent. This is what the agent would choose to perform, and he would do that according to a plan which will result to the stated goal that he wants to achieve. So basically, intentions are desires which the agent has commitment. So the agent has already commitment, for example, to buy the car. And there is a goal there. The goal is a desire converted to intention that has been adopted for active pursuit by the agent. And these are quite unique features, attributes, which contribute to the achievement of a desirable distributed AI framework. And we will go through some particular examples to show some of the benefits we have. So basically, we've also extended our agents. BDI-X agents are extended agents because we wanted to utilize in the beliefs any other type of AI ML or any optimization objective for better understanding of the surrounding environment to the agent. And also, we can enforce prioritization of the execution order of the desires based, for example, on alarms. So if I'm a device and my battery is drained a lot and I have only 10% battery, I don't want to act as a relay for somebody. I want to be excluded from the relay option. So we can prioritize the order of execution based on events, alarms through the system. So desires may depend on the completion of others as well to start or conclude, and thus the priority values are assigned to control their execution. And we also have to somehow guide the agents and keep them within a reasonable framework, a reasonable plan. So there is a plan library which controls the execution of the desires to intentions and restrict the agent deliberation. So this can be changed at runtime, so either an operator or a user can change that, that deliberation and force other plans to be executed instead of the present one. For example, there is a security alert. Now I have to go into another mode. So this specific framework can achieve specific tasks or requirements in 5G6.3 through the distributed agent communication. And we can see an example here in this particular example, the mobiles are the independent devices. And we can use targeted modules within the PDIX agents based on the DAI framework. And the modules can be substituted or added as needed. So we can, during execution, be more dynamic and adapt to the environment as needed. We offer also intercommunication and collaborative decision making by using well-defined PDIX agents in the framework. And this can use many of the predefined well-structured languages for PDIX agents, for example, FIPA ACL. We can include well-known types of messages, propose, notify, inform, or whatever is part of that. So to recap, the constituent components of the framework are the beliefs and the desires, as we mentioned before. There are plans that are associated with the desired, and based on threshold values and events, we can modify desires, plans, and the priorities. And there is a plan library which handle priorities of desires to become intentions. So this is the framework that and the constituent components. And the beauty of this framework is that we can add or remove at runtime whatever modules we would like or modify as needed to handle dynamic events. So I'll go through some of this implemented PDIX agent architecture. The basic parts of the PDI, as we said before, this framework is fully implemented, and we can share it with anybody that wants to have access to it. It may look a little bit difficult now, but in reality, the implementation is not that difficult. All these are lists or databases and some logic around them to create the PDI agent intelligence. So the main modules, as we said, are beliefs, desires, intentions, which can lead us to goals and actions which will act on the environment, and sensing and events can drive this system. The beliefs basically are variables representing the environment state. For example, in our case, it could be the available frequency bands in a mobile device. I may have Bluetooth, I may have wireless LAN, I may have terahertz bands, etc. The neighboring agents, channel quality, or whatever the environment state is, and our beliefs are about that environment. The desires is what the agent would like to do, as we said before. For example, we would like to keep the signal quality at all times at acceptable levels. That's a noble desire, but we have to see if it's achievable. So a desire is triggered by filtered events, so through the beliefs, through our knowledge of the environment. And the device may be connected to the best related device, for example, towards the base station. And it can be prioritized to become an intention. So the intentions basically are all the current desires, and they may be quite a number of them. I have an intention to buy a car, to buy a house, etc., that our agent has committed to pursue. So even though there are many intentions, we have to somehow prioritize them and somehow work through plans, specific plans which will affect my environment. So PDIX agents prioritize the order of execution. For example, they may use any type of logic. We used in our system fuzzy logic because fuzzy logic allows us to handle better the uncertainty of the real world. And we have a plan library which will set specific priority values for the desires. So how do we select which intention to run? Well, that's again based through a queue which stores the intentions and based on their priority, which is already set, as we said, by the filtering before, then we can set the order of execution of the desires. So this is the basic architecture of the implemented PDIX agent, and some other aspects of it to allow for intercommunication and handling unexpected events are added to complete the framework. So what we see here is the complete framework. As I said before, it may look a lot more complex than what it really is. In reality, we have this implemented and can be shared with all. So if we look at the complexity, basically the complexity only depends on the implementation of the fuzzy logic controller and the complexity of the individual plan that we're currently executing, because all the other components are just queues or lists and are part of the object called PDIX agent. And the fuzzy logic, as we saw before, it's only used when we've got infrequent calls to filter these aspects and prioritize. And it could even be order of n execution, especially if it's implemented as a table with parameters. So many appealing features are included in these PDIX agents, and they stem from the agents themselves. They include modularity, distributed AI, multitasking, execution, autonomicity, dynamicity, etc. So there are many, many appealing features to these agents, and many architectural characteristics like persistence, coefficients, priority values, flexibility, responsiveness, and reactivity. And we can go through all of those. I will provide a set of the slides through Professor Rahul, and he can share with you if you're interested in more detail. So if we now look at what it can offer us as a communication network, basically our network control can become much faster with a lot less messaging through the intercommunication of the agents and the independence of the agents to act locally. We can support self-healing mechanisms and act collaboratively to promote the concept of a self-organizing network. And we can capitalize on any existing mechanism implementations because we can fit them into the framework as needed, even if they're artificial neural networks or optimized functions as they exist. So now I would like to go through a very brief example just to make these concepts a little bit more real. And I've chosen the D2D setup, which is what Iakovos has done in his thesis. The device-to-device setup is a nice setup to talk about because the devices themselves are distributed by nature. We have them with us, they're all over the place, so it would be a nice concept to consider. And it's a concept that's required for 5G, 6G. So since it's a requirement for 5G, 6G, we thought we would investigate this a lot more. So a simple example for the realization of this, the D2D, is shown here. Basically, what D2D is, it can operate in both licensed, that is the D2D in-band or the 5G, 6G frequencies, as well as unlicensed spectrum, which could be our wireless LAN type traffic, Bluetooth, whatever technology there is. So we can have any type of spectrum that suits us now to utilize. It's transparent to the cellular network, so we don't need the base station to be a part of the communication. We can be locally independent. It allows proximate devices basically to bypass the base station and establish direct links between them. And it also allows us to offload data away from the base station, for example, into a wireless LAN if it's more convenient to do it now. So it also allows us to take care of devices which might be at the edge and will go out of coverage by allowing them to communicate locally with other devices. There are many benefits to D2D, including better power consumption for the whole network, better spectral efficiency. I'm not going to go through all those benefits, but it's a given that there are many benefits in D2D for 5G and 6G. That's why they're expected to play a major role in there. However, to implement D2D, we have to go through quite a number of challenges, including device discovery. How do we know and where are there devices? The mode selection here is whether we want to choose, for example, the 5G or 6G connection, or we want to offload into a wireless LAN or even a Bluetooth connection. We have to manage interference. Even though we allow less power locally to be used, we can increase the interference locally, but reduce the overall interference for the network. We can manage better the power because we are using less power in the closer proximity. Security aspects, RRM, radio resource management, etc. There are many challenges. We will only look at one specific one, just to make the whole thing a little bit more closer to understand. Basically, in the PhD thesis of Iakovos, he has implemented plans for all those challenges. And in addition, some D2D challenges are handled when specific network events are raised, or some beliefs change due to sensor readings or raised events. So if we recall, the PDIX agents are characterized by the components we mentioned earlier: beliefs, desires, intentions, and goals. And we'll see some of this. And the behavior through perception and plan. So let's go through a particular example now. We consider a D2D scenario, as we said. So if we look at the beliefs that we have, they could include the channel and its quality, the transportation mode. For example, if we're going to go through a relay, a cluster, a relay hop, or some other type of network, the technology used, the location, the neighboring agents, etc. So this is what beliefs we have as an agent, a PDI agent, sitting on a device in a distributed fashion. And we do have a number of desires. We included only a few here. For example, find the best transmission mode that will give us the best achievable signal quality and data rate. So in terms of transmission mode here, it could be that I want to use the existing 5G connection to the base station, or I want to go through a D2D device, or I want to offload to a wireless LAN or whatever. And another desire would be the data rate is acceptable. I want to use this device to carry some video data, so I need some acceptable data rate and some acceptable signal quality. These are desires that I have. That doesn't mean I can realize them, but when they become intentions, I would like to plan and go through the plan to execute them. So when the desire, for example, find transmission mode with best achievable signal quality and data rate reaches a priority value of 100%, then this is converted to intention and it's moved to goals. So in the goals, the intention will run as a plan. And we see in the next slide a simple example of a plan. So the plan basically would take us through a number of steps. The first step here is the desired device discovery to become an intention. So a new device comes within the reach of some other devices and wants to use a D2D communication to connect to them. So once the desire here is fulfilled, the priority value of that desire is set to 0%. It's done already, while the rest of the desires priorities are increased. Step 3 is to have an acceptable data rate, and that becomes an intention we want to pursue. And step 4, there is a specific plan for this. For example, we want to compute the weighted data rate of all the proximity devices and select the highest among them. We want to set the transmission mode as D2D client and initiate a connection to a D2D relay with the highest weighted data rate. We will request a connection to the relay. We would accept a response, and we would have the D2D client connect to the D2D relay and achieve the communication through that mode. And once this plan is finalized and the intention is achieved, the priority value of that related desire is set to 0%. Then we can look at another desire, select another one if there is any, based on the priority values, which becomes an intention, and so on. So this is just giving you a brief snippet of a plan that a PDI agent will be executed on this particular example where there is a new device entering the network. Okay, I think we can skip this one. Let's have a quick look at some of the evaluations results that we got for a specific scenario. In this scenario, we have the number of devices in a cell ranging from 10 to 1,000. They are placed in a cell range of 1 kilometer radius from the base station, and we use a normally used distribution to place these devices. The simulation environment is implemented in MATLAB, and we use specific libraries from MATLAB 2028. There is a specific 5GLT toolbox there with JADE library. And we evaluated comparatively this distributed AI approach to several other AI approaches or common approaches. In terms of data rate, less power and less time, we could show through these particular examples that it outperforms considerably all other approaches, and there are details in the thesis as well as some publications we have in the literature. And in terms of its performance, again, DICE is that particular plan, distributed AI plan for the device-to-device, and it outperforms quite a number of other competing approaches, as we can see in this view graph, in terms of PC efficiency, power consumption efficiency, spectral efficiency, clustering efficiency, decision delay, and signaling overhead efficiency. These are desirable features that we'd like to have. Basically, to conclude, we have introduced a novel agent-based distributed AI framework which can address the demanding management and control challenges in 5G, 6G. We introduced this PDIX agent architecture and its constituent elements. And from the D2D implementation examples we have shown that the framework executes control of the communication, achieves fast decisioning control, is dynamic and flexible. We have other examples where there is device mobility, and it comparatively achieves a better solution in terms of spectral efficiency and power consumption, as well as reducing messaging exchanges or making the reaction to events much faster. So some future works and thoughts for collaboration. We are currently looking at a way to have a small-scale testbed to test our AI agents on real devices, and also do other plans and intentions for tackling 5G and 6G challenges. On the theoretical side, there is also work to be done to improve the PDIX agents. One aspect we have now is that whatever an agent sends to another agent is accepted by the receiving agent. So there is full trust between the agents, even though the agents run on individual devices which are owned by individual entities, other entities. So there is a need to improve both the privacy and security, but also perhaps introduce a game theoretic perspective where there is some personal incentive onto the agents introduced. So that's also a very interesting aspect to look at the non-cooperation environment. And obviously, we can introduce new technologies, D2D caching, software-driven functional metasurfaces, blockchain technology, NFVs, and any other new technologies. So all these are some brief thoughts. We're very open to your thoughts, of course, to your ideas. And we have some expertise with the framework we would like to share with you. We have the framework implemented, and we're very open for any suggestions, discussion, questions that you may happen to have. Either now or later, we can address those Zoom, Skype, emails. But for now, if there are any specific questions, we can answer them. And then I will spend a few minutes for the 5G, 6G vision mainly.
Any specific tested software that you have been selected so that we can test on simulation?
Yeah, I think the first step was to buy a software-defined radio. And I'm not sure what they've procured. It might already be there. The devices are all the devices that we have. So the idea is to implement them on Android devices. They're easier to handle, more open. So that's the plan. There is already a number of devices which have been purchased. And Iagovos is already working with some people to implement those on the actual devices. So the software-defined radio, and they will act as a base station, and they are procuring a 5G, I think, base station for that. So it will be one single cell, short power, lab power type, and a number of devices. That's the envisaged scenario.
Organization of that cell in that organization of a cell.
The cell will be 5G, as I said. We'll have a 5G cell, but we'll have also Bluetooth and wireless LAN. I don't know if that's the thread of the question. We have multiple modes. The device.
The framework that you have designed is for one-to-one devices.
Yes, it's not necessarily one-to-one because we're doing clustering and everything else. It's possible, but the agents run on one device. So every device has to have its own agent.
Relationship also, one-to-many, many-to-many.
We haven't explored those. But there is, in the aspect of clustering, we need to consider one-to-many. I'm not sure. I think possibly Iagovos also tackled that because he's been doing a bit on clustering.
We already discussed about this thing, the antennas ones and one-to-many. So we can look forward for this.
For this, okay. We'll do that once I get back. We'll organize with Iagovos to have a Zoom chat. That's excellent. Any other suggestions or questions, clarifications?
Sir, since I am new in the field of metaverse, so I just wanted to know how we can perform the evaluation that is regarding the performance of the 5G and 6G in the metaverse environment.
In the metaverse environment, I'll speak about it in the next talk a little bit.
Okay.
And then we can discuss any issues about metaverse or anything you would after that, if you
Does
don't
that
mind.
also have the information about blockchain technology in 5G and 6G?
We haven't worked on blockchain yet, but obviously anything we do now will require blockchain. In terms of the distribution, we would like to introduce blockchain as well as everybody else. In terms of the power system that I mentioned earlier with the Sahijabyte from Japan, within that framework we are building the blockchain from the beginning, from the start of our project.
So your topic says that it overcome the issue of scalability, since the blockchain technology has a huge drawback. It is not scalable, like not up to the scalable, since IPNX and IPFS is doing some work, but it's not still scalable. So can this technology be be helpful in the terms of scalability in blockchain technology?
Yes, that's what we expect, and one of my colleagues has done some work on that, and the early results are promising. We can introduce you to the other colleague if you're interested about
Yes, sir,
blockchain,
I'm very
because
much interested.
I'm not a blockchain person, I just hear the buzzword, and that's about the
Yes,
extent
sir.
that I
That
know.
would be great if you introduce me to the
Yes,
people.
please send me an email,
Yes, sir.
and we'll link. And that other project is very interesting as well. It's not in communication networks, but it's in power systems. And the idea is the same. We've got a distributed system of devices there that consume power.
Yes.
We've got a distributed system now of producers, and somehow you have to match the two and match the flows,
Yes.
so you have a stable system.
Yes, sir.
And there that's where we're looking at introducing this blockchain within the whole framework.
And can you tell which framework they are working on? Either it's Ethereum, Hyperledger, or any other layer 2 device? No, sir.
No.
It's
So,
okay, sir.
yeah, we'll
Yes,
we'll
sir.
do
I
the
would pretty
individual
much like
talk.
to talk to those researchers.
Yes.
Yes, sir. Thank you so much.
Pleasure. Okay, I put the slides. Zoom quit unexpectedly. We won't bother with Zoom, sorry. So I put the slides very much in a hurry a few days ago. I apologize, going to be a bit here and there. And I based a number of input from my good colleague Ian Akildis. He's done a lot of work on 6G and beyond. And I shared a number of his whatever driving, assisted driving, smart, anything smart is being talked about that it will be supported by this new technology, 5G, 6G. And there are many, many emerging use cases. One can draw thousands of these drawings. I borrowed this from Ian Akildis' talk. Basically supporting any smart system that would like to think about in the future, extended reality, augmented reality, mixed reality, metaverse, you name it, it's all part of these emerging use cases for these 6G systems. And of course, when we come to networking, we would need ubiquitous intelligent information networking. So we have to do new network multimedia, including holographic support, even holographic networking. We would need to handle new interfaces as part of this new heterogeneous radio network, including flat architectures, cell-free architectures. We have to integrate both terrestrial and aerial networks. You see many papers talking about UAVs. So if I start from the beginning for this one, is 6G will definitely need to tackle new intelligent networks. So we have to find ways to handle new network multimedia, including holographic images. We have to have the ability to manage heterogeneous networks in all its true sense. We have to handle new architectures that we haven't been able to handle in the past, including cell-free. We have to integrate both terrestrial and aerial networks, including UAVs. The UAVs can act either as users, consumers, or even they can act as part of the infrastructure on demand. They can support the base stations in case there is no connectivity, for example. We can place the UAVs in areas where they can cover holes in the radio support. Basically, we need to handle these new types of architectures. And of course, there is a new fusion now, which is everybody talking about. We have to integrate or fuse together communication, computing, control, and sensing. So we have to look at all these together. In order to do that, perhaps AI is necessary, as we've seen before. And we've seen this table before of the key performance indicators. The figures we're talking, especially at 6G, they go into astronomical figures in some cases, terabits per second, gigabits per second for data rate for to be experienced by everybody within a network. Very high spectral efficiency, very high bandwidths when we go to terahertz especially. The traffic capacity to be in gigabits per second per meter squared. Very high connection density, 10 to the 7 devices per square kilometer. And incredible energy efficiencies and latencies. I mean, to talk about 100 microseconds latency, I don't know how we can achieve that. But nevertheless, that's the goal of the people that are talking now about 6G and the visionaries for 7G even. We're talking about these low latencies. And these low latencies, in a way, they are dictated by metaverse, by augmented reality, by extended reality, mixed reality. And a big reason for that is because we need those to have an uninhibited experience with extended reality. Otherwise, you have something that's called motion sickness if you don't stream your images fast enough. So we think these are necessary, but maybe not to these extreme figures, but we'll have a network that will be very tested. And reliability goes without saying. If we're going to become a part of the network, and the network is going to become a part of us, and we're going to live in a digital world, and we're going to be immersed in a digital world, then we need 100% reliability, and we see it anywhere we go. If I lose my phone, I don't know what I'm going to do. I lost my credit card, and it was okay. I managed to survive that, but I don't know how I'll survive losing my phone now, even before I am fully immersed into that digital world. Jitter, mobility, we're talking about and reconfiguration in real time are all going to be important aspects. And if we focus on only one application, I'm not going to focus on others, but that's indicative of what we expect. Metaverse is a well-celebrated vision for 6G, of course. And meta is a word from Greek. It's beyond. Meta is a very common word now for meta surfaces, meta verse, meta whatever. And this vision of the metaverse originated in the science fiction Snow Crash by Stephenson in 1982. Basically, what is a metaverse? It's a network of connecting physical and virtual worlds seamlessly. Whatever that means in our life, I don't know. We'll find out. But basically, we will be immersed into the digital world. We'll be a part of it and vice versa. And the separation between the two is blurry. In terms of the separation between the two worlds, it would not be any visible, as we said. The mixed reality will be realized thanks to the convergence of some key technologies. And these are in terms of extended reality, virtual reality, augmented reality, mixed reality, hologram type communication, and of course, we need a supporting network. If we're going to offer that, the network has to be 100% reliable and has to offer those metrics as we saw before. So if we put some figures and numbers to this, you can see what the real problems are. So if we're talking about data rates, for video, today we have video that, especially your generation, I mean you younger generation, us oldest remember, not possible to see a video on our phone, for example. YouTube now, you just take your device, you press the button, there's the video. A few years back, it wasn't possible. We're talking about data rates which 10, 15 years ago were not possible. So we're talking about data rates 35 to 100 megabits per second to be offered by 5G, not a problem. We're talking about latency in terms of milliseconds. Again, our networks are capable to give us now synchronization in audio and video, and we have smart devices and computers which support video. In terms of virtual reality, we have a quantum leap. You can see here the 35 megabits per second, it's a very low bandwidth for VR. We're talking about gigabits per second if we want to have an obtrusive virtual reality. Mixed and augmented, the same story. And in terms of latency, 20 milliseconds for virtual reality, 10 milliseconds for mixed reality and augmented reality. And if we go even to holographic type communication, we're talking about terabits and microseconds delays. We have to synchronize in the distance of a video between two streams. Now we have to have multiple tiles and thousands of use of sensors in a holographic type image. And in terms of devices, we have now already smart devices, computers which unobtrusively show us video. We press the button, there it is. Head-mounted displays for VR, which cope at least locally with what we are seeing in VR. Smart glasses are already in the market. And of course, when we come to holographic type communication, we have already some technology that's there. So in effect, all these metaverse applications will place significant demands on networking, computing, and communication. All of them have to come together, including sensing, as we said before. And today's networking technologies cannot support this. In terms of services, therefore, if we look again at metaverse, extended reality, holographic type communications, for example, there are plethora of applications we can think around metaverse. So we see some here in various industries, from telepresence, healthcare, education, etc. One can add, of course, all their own spots in there. It's up to you to decide what type of applications you want to offer through this metaverse. And of course, we need the technologies which will support metaverse. And one of the technologies is, of course, 5G, 6G, which will have to be able to support this type of technologies. Security, privacy, trust, AI, and ML are all integral parts of what we envision in the future will be necessary to be offered as part of our technologies. So achieving the key performance indices we saw before, it will need revolutionary breakthroughs across all domains of wireless communication. We'll have to use new spectrum for sure. We have to go into the terahertz perhaps. And new radio design paradigms. We have to have novel radio designs that can simultaneously send and communicate the entire electromagnetic spectrum. We have to have novel networking architectures, including flat structures, cell-free to minimize the delays, because if I have to go through a base station, immediately my signaling and my delay increases. And we have to introduce this into the very fabric of the environment to scale to meet the area traffic capacity and connection density requirements put forth by 6G. And we have to increasingly use intelligence and automation. So all these will help to build an autonomous network which will be reliable, which will support the envisaged application scenarios which we saw earlier. And basically, we saw this view graph before. This is only a small subset of what we need to offer in terms of technologies. There will be others, I'm sure, in the next 5 to 10 years. And that's the view of 6G. We're looking at 2030 as a kickoff point, let's say, for 6G technologies. And this will need to include, of course, terahertz band. And we all know the terahertz problems in terms of propagation loss, obstacles, etc. But terahertz will give us abundant spectrum resources. We need to provide intelligent or even programmable wireless communication environments. In this space there, we can mention reconfigurable intelligent surfaces, programmable wireless surfaces, whereby we manipulate the electromagnetic waves in a way that suits our environment. So we can, in effect, shape every electromagnetic wave that comes in our environment in a way that will suit us. Maybe focus it on a particular device or block it totally, absorb it totally so it doesn't interfere. So we'll need to go towards these new technologies. We need to offer pervasive AI with large-scale network automation, which will demand distributed AI. We need an all-spectrum reconfigurable front end for dynamic spectrum access, cell-free, massive MIMO, that's buzzwords that you see, and we need a holistic approach to security and privacy, which are increasingly vital for the adoption of these technologies. So in conclusion here, I would say that 6G is an exciting area of research. We're starting fresh now. 5G is already been implemented, and we heard earlier that it was the inauguration day here, very momentous time. It's appealing as it's currently being shaped now. So it's shaped by the research, us, and the industry communities. So there are many interesting research questions that will need to be answered to get there, and there is scope for new breakthroughs, ideas, in order to meet that. And that either as a PhD candidate, or a postdoc, or an academic, or even a guy that links to industry, we need to get together to come with these new breakthroughs that will give us the demanding key performance indicators that we mentioned earlier. So I think I'll leave it at that as a very brief intro to 5G, 6G, and metaverse more in particular. As I said before, we can have private discussions for further depth. Thank you.